Hello everyone, this is Fundamentals of Micro and Nano Fabrication. My name is Sushobhan, I am from IIC Bangalore, and today we are going to talk about cleaning recipes. In the last lecture we looked at what is a clean room, why do we need a clean room, what are the various techniques we use to keep clean rooms clean of particles and chemicals so that contamination does not fall on top of our wafer. However, contamination does always fall because practically no matter how clean a clean room is, there are always particles. So, we need to find a way to remove those particles, remove that chemical contamination before critical processes, and that is the subject of this lecture. So, this is an example of a study that was done to track contamination on top of wafers. So, you start with a starting wafer and that starting wafer is extremely pure. However, as you do consecutive processing steps on it, as you make a device on it, as you go from left to right, by the time you get to the end, you will see that the number of particles on the surface have accumulated. This is a problem, this is a known problem that faces any fabrication step. So, before critical step, you have to find a way to reduce this contamination, and that is what you use cleaning for. Now, what is a critical step? A critical step is any step in a process that has the maximum impact on yield. In the last lecture, we looked at the concept of yield and why yield is very important. So, any process that reduces your yield is a critical process, okay, or can significantly reduce your yield is a critical process. Typically, these tend to be high temperature processes, processes where the wafer sees high temperatures. Why that is better understood when we discuss diffusion. For now, we will just let it be. All right. So, how do we do cleaning? There are several recipes or chemical mixtures that are used to do cleaning of wafers. Most of this lecture is focused on silicon because that is the workhorse, though I would also touch on what other substrates can use. A lot of the time the other substrates also tend to use the same techniques and chemicals, so it is illustrative to understand how silicon cleaning works. All right. So, let us first look at the first piranha we are going to look at is what is called piranha clean. It is also called sulfuric perovskite mixture or SPM, and what it is, it is a mixture of a peroxide which is hydrogen peroxide and sulfuric acid, concentrated sulfuric acid. It is used to clean organics and gross particulate contamination. It also strips photoresists. It is a standard process for cleaning silicon germanium wafers because silicon germanium wafers are not compatible with the next clean I am going to talk about. So, this is the primary way to clean those wafers, and it is also used as a pre-clean before the RCA clean. RCA is the next clean we will discuss. The recipe is fairly simple. You take concentrated sulfuric acid, which is 98% sulfuric acid in water, H2O2. Typically 30% H2O2 in water is a stable mixture, so that is what we use, and these two are mixed in a ratio of 4:1. Just to be clear, in the semiconductor world, the molarity and other sorts of concentration measures are not popular. People typically give recipes in these 1:2, 4:1 type of ratios. What it simply means is you take the 4:1 means you take the 98% sulfuric acid 4 parts and you take the 30% peroxide 1 part and the mixed 2. Okay. So, there is no molarity concentration, there is no weight by volume percentage, etc. This is the common way specifications are given, partly because we are electrical engineers, electronic engineers, material scientists, we are not chemists. The temperature of the mixture is often kept at 120 to 80 degrees C. In general, you want to use the least aggressive recipe, and that brings us to the first concept that I want to highlight. So, any cleaning recipe is fundamentally an etching recipe, right. So, you are trying to etch something, you are trying to etch the contamination on the top, but that etching may also etch the silicon or the structures that you have fabricated on top. So, there is this weird curve where the cleaning energy density, so there is a damage threshold where if you increase your energy density of your cleaning solution, you will start causing damage, above which you will start causing damage, and then there is a cleaning difficulty curve where you need to provide a certain minimum energy to do the cleaning in the first place. And the difference between these two curves is your operating range. So, your cleaning methodology needs to be within this so that it does not cause damage, but still does the cleaning. And as the semiconductor generations have progressed, the distance between these two curves becomes narrower and narrower because you are making structures that are flimsier and flimsier. And the sweet spot of cleaning that is right in the middle is harder and harder to achieve. So as much as possible, you like to remain closer to this green curve. You don't want to do very aggressive cleaning. So as much as possible, try to use the most dilute version of the cleaning solution. And that is a constant that I would say again and again in this lecture. What is the mechanism of this clean? The H2SO4 is an oxidant. It reduces organic to carbon, and that carbon then gets oxidized by the H2O2, which converting into carbon monoxide or carbon dioxide, which leaves the solution, and thereby the organic is removed. There are certain side effects of the Piranha etch or SPM etch. It will etch metal. So if your samples have metal on them, you should not do Piranha clean. It also forms a 1 to 2 nanometer thick oxide layer on the silicon surface, and that is because the silicon also gets oxidized by the H2O2, and the thickness of that oxide is 1 to 2 nanometers. It's a weak quality oxide. It's called a chemical oxide. It's not useful for any electronic application, but it does form. What are the problems of this? It's a very exothermic reaction, so you have to be extremely careful. In fact, when I say 80 to 120 degrees C, the solution tends to be self-heating. So even if you don't heat the beaker or the bath extrinsically, just by the virtue of mixing peroxide and sulfuric acid, the whole solution will heat up. The larger the batch, the more heating up. The other thing is this mixture actually rapidly consumes the H2O2, so it releases the oxygen. So you need to make this a fresh solution every single time. There is no, you can't make a batch and then keep it and use it over a week. It has to be made fresh right before the experiment, or at least the first thing in the morning. And it is an active for some variable time, say half an hour, 1 hour, something like that. It is incompatible with metal coated wafers. We have already discussed that. There are certain exceptions like chromium and other noble metals which tend to not get reactive with sulfuric acid. So in those some of those cases you can use this clean. The high temperature evaporates water, so the concentration of sulfuric acid actually changes in the system. So the process control is not very good. And it also does not clean very hardened resists. Hardened resists that have become very hard because of other processing. The word hardened will be better defined when we discuss lithography and etching. There are some modern variations of this where people have started using ozone instead of H2O2 for cost reduction, for better control, etc. We'll come to the modern version of these cleans a little later, so I'll discuss it then. The thing I want to highlight, however, is that this is a very aggressive chemical. This is a very aggressive mixture. It is more dangerous than sulfuric acid alone. So you have to be extremely careful in managing this. You always wear PPE or personal protective equipment, which is nitrile gloves, splash goggles, face shields, chemical aprons. You always do remember the standard rules, such as always add acid to water and not the other way around. This is a refluxing acid. This is a boiling acid. It's very dangerous. Please stay safe and disciplined. The next clean, and this is the workhorse, by and large used in the industry and also used a lot in research and universities. This is the RCA clean. It was developed by Werner Kern in 1960s. Actually, I would urge you to go and read Kern's original paper. It's available on the internet. I think it's very insightful to actually read it and understand the thinking behind the developing of the clean. It is a gold standard for wafer cleans. It's a 2-step process, or if you want to say a 3-step process, and it must be used before all critical steps in silicon processing. So the recipe is, the 3 steps are, it has an SC1 step which removes organics and particulates, it has an SC2 step which removes metals, and then there is a step to remove the chemical oxide that always forms on the top. Just to reiterate, RCA clean is also very dangerous. It's a more dilute acid, so arguably less dangerous than Piranha, but still very dangerous. So please wear personal protective equipment whenever doing RCA clean. For very dirty wafers, often Piranha clean serves as a pre-clean for the RCA clean. So you would do it before the RCA and then do the RCA later. Okay. So let's look at SC1. It's also called RCA1 or an alkaline peroxide mix or an APM solution. The recipe is ammonium hydroxide, 27% in water. This is the stable form. H2O2 again 30%, and then the rest of it is water. And these are mixed in a ratio 1:1:5 or 1:2:7, or even more dilute versions in some cases. The temperature of the solution is around 40 to 80 degrees C. It does not self-heat as much because there is a lot more water in this. So you have to externally heat it either using a hot plate or through a bath. And typically you do this clean for 10 to 15 minutes, which is the same as Piranha before. The mechanism is similar. H2O2 oxidizes the metals, some metals. Ammonium hydroxide forms soluble complexes. We'll look at that in the right hand side. So certain metals, certain transition metals such as silver or copper or zinc, they tend to form complexes. So here is an example. So silver gets oxidized into Ag2O. Ag2O reacts with ammonium hydroxide to form this ammonium complex, and ammonium complexes tend to be very soluble. So silver oxide on its own is not soluble in water, but the ammonium complex is. Similarly, copper oxide is not soluble in water, but the ammonium complex is. So the formation of this complex allows you to make a soluble version of this contamination that you can then wash away. If you did not have the ammonium, just have the silver oxide, then it would not be soluble, it would just precipitate on top of a wafer. So even though you have oxidized it, there would be no way to remove it, right? So solubility is the key. And then the OH ions also help in removing the particles. This is a basic solution. It removes particles very similar to how detergent or soap removes particles from your body. Right? A little caveat for safety and environmental: ammonium complexes, because they are very stable, are big environmental hazards. They are bioaccumulative, they are persistent, which is that they are long lasting, and they are toxic. So especially if you have a lot of copper contamination or Ag contamination and you are using RCA to remove it, whatever you form needs to be treated as a hazardous waste. It should not be thrown away down the drain, it should not be thrown into the water supply or the sewer. It will cause things like Alzheimer's, Parkinson's, cancer, heart disease and autoimmune issues. It's a very, very bad chemical to throw in the environment. So please refrain. So how does SC1 actually do particle removal? So we have looked at how it removes certain metals by forming complexes, but how does it remove particles? So I hinted before that it does it in a very similar manner to how soap does it. So either the particle gets oxidized with the H2O2, in which case you just chemically converted it off, or the particle remains in its form, but then the zeta potential of the surface energy of the particle changes because of the OH ions, and there is electrostatic repulsion between the surface and the ion, and the particle goes away. This is exactly the same way the soap works. So or how certain basic solutions are used to clean glass. So this is exactly the same process. A side effect of this is that you do leave behind a thin layer of oxide because the H2O2 is there, so you do leave behind a thin layer of oxide that forms on top of the silicon. The particle removal efficiency depends upon what dilution you are using. The more aggressive dilution tend to be better at removing the particle. However, once again, you have to be careful, because when you increase the concentration of chemicals, the probability of damage or roughness increases, and at the same time the cleaning efficiency reduces, and again you are looking at this sweet spot in the middle. You want the things to clean, but you do not want the things to get damaged, and this becomes a challenge, right? So you have to play with different concentrations. Start with the lower one. If it's not getting clean, go higher. The other thing is the silicon ammonia actually does cause some amount of silicon etching. It's a base, and basic solutions etch silicon, and that does lead to damage to very small features, or very small, and or might also cause something called micro roughness. So even though you start with a smooth surface, if you leave it in ammonium hydroxide, it will start to roughen up. So that can be prevented also by going to lower concentrations, but at the cost of lower cleaning efficiency. Just like Piranha, APM solutions also degrade with time. So if you start with the concentration of normalized concentration, if you look at your normalized concentration, within 40 minutes or so, you're only 10% of the solution is left. So the only way to do this is to make a fresh batch every single time. It takes a certain amount of time to just heat up the solution to around 80 degrees C. So then say 10 to 20 minutes, and then you have a window of 10 to 20 minutes in which you can use the solution, after which it is spent. Yeah. So you can't make it or store it in advance. The other next step in the RCA is SC2 or RCA2. This is a hydrochloric perovskite mixture. It's called HPM. Just like the previous one, it has peroxide and water in 1:1:6 or 1:2:8 ratio, and the ammonium hydroxide, instead of ammonium hydroxide, you have now put HCl. 73% is the standard that we get. And again, you heat this to around 70-80 degrees C and you leave it in the solution for 10 to 15 minutes. The mechanism once again is similar. It is just acidic solution instead of an alkaline solution. H2O2 oxidizes, then HCl forms soluble chlorides. So, here is an example. Supposing you have some sodium or zinc or aluminum or iron, all of these react with HCl to form these chlorides, and these chlorides tend to be very soluble. Okay. So, these chlorides are soluble. So, you just virtue of washing the wafer later, you would end up removing this contamination from the surface. This also leaves behind a thin layer of oxide on the silicon surface because of H2O2, just like the previous two cleans. Okay. What are the problems? Once again, there is surface roughness, especially at high H2O2 concentrations. Very similar to what I have said before, there is this trade-off between cleaning and probability of causing damage, and you want to be in a sweet spot. The industry has, for cost savings and for other reasons, has tried to migrate toward lower concentration of HCl and try to replace H2O2 with ozone. We will talk more about this a couple of slides later. Once again, the reagents get consumed with time, you can't store it, you have to make it fresh before use. Okay. A little bit more about the mechanism behind the HPM clean. So, if you look at the silicon surface, there are two things that can react with It is the silicon, which can form silicon dioxide, and you have metal, which will form the metal ion. So, this is an electrochemical reaction. So, which of these will occur will be decided by their oxidation potential, the standard oxidation potential. And in general, if you do not have any other reagent in the solution, if you just have water, in general reaction 2 is driven to the left, which is that the metal plates out, and reaction 1 is driven to the right, which is the silicon oxidizes. That is because the silicon has a tremendous tendency to oxidize. So, silicon wants to oxidize, and that forces the metal to reduce, which is why you actually get contamination. Now, in order to prevent your metal from forming on top of the surface, what you need to do is to add some other reagent, which is what the cleaning reagent is. So, for example, when you add hydrogen peroxide, this is the hydrogen peroxide, and if you look at its standard oxidation potential, it is fairly deep, it is very low. What that means is it's a very strong oxidizing agent. So, that oxidizing agent will oxidize everything that is above it in the standard oxidation potential table. So, everything above this row will get oxidized. So, the gold will get oxidized, copper will get oxidized, iron will get oxidized, nickel will get oxidized, chromium will get oxidized, and silicon will get oxidized. Okay, everything above will get oxidized. However, things below it will not. But that is not a concern. For most metals, H2O2 will oxidize. And that oxidation is what pushes this reaction to the right, and then that ion can then react with the chloride, form a soluble complex that can be then washed away. Okay. This also tells you something about what sort of oxidation agents would be good. It is good to use H2O2. It might be better use ozone, right? Because ozone is even more of a strong oxidizing agent, and that explains why the industry is trying to move towards it. By the way, I would like to give some credit to Professor Bokoi from EC Waterloo. Several ideas in this slide actually come from his lectures. I would actually urge you to go and look at some of his lectures. They are very illuminating. The last step, and this is an optional step but often done, is that the chemical oxide that has formed on the surface because of the ammonium hydroxide or because of this sulfuric acid step or the hydrochloric acid step can be removed. This is typically done with a dilute solution of hydrofluoric acid in water, very dilute, 1:50, 1:100 is the standard. You do this in room temperature and it just takes 1 to 2 minutes depending upon the concentration. The reason for doing this is fairly simple to understand. You have silicon dioxide, and embedded in this silicon dioxide might be a particle contamination. You put it in the hydrofluoric acid, the oxide goes away, and that makes this particle free, and hopefully it will float away and remove itself from the surface. The problems are it does cause again some micro roughness, so you want to remove it as dilute as possible and keep the times as short as possible. Certain side effects, it does leave a hydrophobic surface. What hydrophobic means, the water does not stick to it. So if you have once you take the wafer out, you will actually see no droplets on it because it's completely clean, the water is not sticking to it. That's a sign that your etch has completed and you should take the wafer out. Okay. And the other thing is that it passivates the surface of the silicon with silicon hydrogen bonds. I like to talk about that for a minute. So once you remove silicon dioxide through ammonium fluoride or hydrogen fluoride, you tend to form this silicon hydrogen bonds on the surface. The silicon hydrogen bond is fairly stable, and this is a sort of a chemical and electronic passivation. The downside is that it just lasts for minutes to hours, simply because ultimately the oxygen from the ambient will react with silicon hydrogen bond and form silicon dioxide again. Practically what it means for the cleaning step is that the cleaning must be done before the critical step, and the time between the cleaning and the critical step must be kept as low as possible, because this hydrogen passivation allows the surface to remain clean, but with time it will degrade, and once it degrades you tend to reaccumulate the junk on the surface. Okay. So my rule of thumb is that the time between the cleaning and the step after it should not be more than 10 to 30 minutes. Let us talk a little bit about some labware that you must use to do this cleaning. Remember, we are doing this to remove contamination. So the labware that we use must be of materials, and the protocols must be such that we do not introduce unintended contamination. So we always end up using quartz or Teflon wafers, Teflon labware. That is what is recommended. Try to avoid colors or pigments. Just use virgin clean Teflon. Try to avoid Pyrex or soda lime beakers. They are very cheap, very easily available, but if you look at chemically, soda lime glass or Pyrex glass is full of boron, sodium and potassium, potassium, and that will cause that type of contamination on top of your wafer. So please avoid those. Try to use quartz beakers. They are available, a little more expensive. The wafer and sample carriers must also be Teflon or quartz only. So here is an example of a wafer carrier. So this allows you to process several wafers at one time. For smaller wafers, you don't need these. You can just use keep them directly into the beaker. We also need some way of manipulating the wafer, either a tweezer or a wand. Please don't use metal tweezers. Please don't use photoresists. Please keep the tweezers clean. Tweezers used to clean the substrate must not be used for anything else. You would always end up creating contamination that will come back to haunt you later. Here is a QR code for from a website that actually gives you some tweezer handling tips. I urge you to go and look at it. So no Pyrex, Teflon is good, wafer cassettes are good. All right. A little more on the tweezers. So it's very easy to go and buy low quality tweezers of unknown cleanliness and unknown quality. I would discourage you. Try to use only Teflon or polypropylene tweezers. Glass filled Delrin, few other brands, a few other material types that are available are not the ones to be used for semiconductor processing. Please do not use metal tweezers. Even these green colored metal tweezers that come with this Teflon coating are not recommended for most applications that require acid or base cleans, because over a period of time this Teflon coating comes off and you are back to square one with metal contamination on your wafer. For more advanced cases, you might consider using a wand. This is just a vacuum wand, so it picks up the wafer using vacuum. And again, some wafer handling tips for a different video. Those of you are interested, I urge you to go and look at it. Okay. Have certain discipline when managing wafers. Only hold the edges, never touch the middle of the wafer, only the edges. Do not breathe on the wafer. Make sure they are far away from you. Do not put them on dirty surfaces. Do not touch them with fingers. It's very, very hard to remove all contamination from a dirty surface. Finally, one slide on rinsing. Now, this seems obvious. Before every cleaning step before and after is there is a rinsing step. But often people don't quite understand how important this rinsing step is, because this is the step that actually cleans the surface. see, all the chemistry that we have done has still the contamination is still in the solution. The way we remove that contamination is to actually do the rinsing. So please don't get lazy in the rinsing. Be very particular. If the recipe says rinse 3 times, rinse 3 times. If the recipe says rinse 5 times, rinse 5 times. The way the rinsing works is just cleaning by dilution. So every time you rinse, you probably are reducing the contamination level inside the liquid by 10x or so. So 5 times or 6 times rinsing is trying to reduce the contamination by 5-6 orders of magnitude. There are certain automatic dump rinsers that you can use if you have several wafers. They are a little more expensive but available. If you have small pieces or single wafers, you can do this in beaker itself. Okay. Lastly, once you are done with rinsing, there is typically a step of blowing dry the wafer. Please pay note to the word blow. The idea is not to dry the liquid on top. The idea is to push the liquid off the wafer onto some absorbent cloth. So you don't want to dry the water, because when you dry water on a surface, you tend to form stains. So for example, this is what I call coffee rings. So if you have ever noticed coffee that dries on top of a table will leave a stain. Why? Because there is a certain, because of the solution, there is a certain solute that is in the solution. So when the solvent goes away, that solute just precipitates out on top of the surface. So if a liquid dries on the wafer, it will form these sort of contamination rings on top of the wafer. You don't want that. What you want to do is push the liquid off without drying it. Okay? So we are not evaporating the liquid, we are pushing the liquid off. So that's why things like nitrogen gun or spin dryers or spin dryers of these two types are often used. Okay, so this is sort of important. A few other wafers do's and don'ts that I don't want to spend too much more time on. We are getting you are welcome to go and look at some of these videos of established groups on how to do this. But if I were to summarize it all, always use personal protective equipment, always hold wafers from the edges. So this is the correct way to hold it, this is the correct way to hold it. Please don't do this, never hold the wafer with hand, and always blow dry. And try to not do this either. You see, you're almost touching the device in the middle, and that's not good. So try to hold it from the edges if you have a small substrate. Okay. And also please don't do this, not good. Any die once touched by hand will always have sodium potassium contamination, which is not good for the device. With that, we'll end here. In the next lecture, we'll look at some more advanced techniques to do cleaning. See you next time.